And in today's webinar, in today's webinar, I'm going to give you a brief introduction into the smooth hydrodynamics method, which is also implemented in LS-DYNA. And the idea is for you to give you as inspiration and to think of LS-DYNA not only as a tool for crash analysis. You can do much more with LS-DYNA than just crash analysis. And that's the idea of this webinar series. Yeah, beyond FEM, there's more than finite element method. My name is Maik Schenke. I'm working for the DYNAmore company since 2017, and I'm, among others, are responsible for the technical support on behalf of everything which is not crash analysis. So if you do something with LS-DYNA which is not crash, it's quite likely that when you write to the support, it's quite likely that you get in contact with me at the end of the day. Okay, so what is the finite element? What's not the finite element method, but what's the SPH method? In general, SPH is a method which is a mesh-free method. I don't want to talk about so-called particle method, because actually it may look like it's a particle method, but actually we prefer more likely to call it a mesh-free method, because it's still based on continuum mechanical equations, but not using a fixed mesh like finite element method, but having particles, and these particles serve as some kind of computational points. So what is the benefit of doing this in comparison to the finite element method, for instance? For instance, you can do large deformations. You have no problems in material separations and material mixing. You just intrinsically already get free surfaces, for instance, water surface and so on. Yeah, so this is a typical example. Impact analysis. This is also a hint on where the SPH method is coming from. It was used to compute the collision of stars. Yeah. In astrophysics, so this is where it's coming from, but now it has spread, or the method has spread in many different applications. Yeah. And in LS-DYNA, it's mainly used for like impact analysis, also water flow, like fluid dynamics, and so on. Okay, a few remarks regarding LS-DYNA. LS-DYNA is a multi-physics solver, so it's not only crash related. Yeah, we nowadays call it more multi-physics solver, and apart from other codes, LS-DYNA has this, I would say, pretty unique one-code strategy approach. Yeah, that means we have everything into one code. Yeah, if you acquire a license of LS-DYNA, you get everything for free. That means maybe you buy LS-DYNA, you want to do crash analysis, mechanical analysis, then you buy LS-DYNA, but you also get particle methods, fluid dynamics, thermal solver, electromagnetism. You get it all. Yeah, it's all covered by one license because everything is built into one code. And the idea of this one code strategy is to make the coupling efficient as possible. Yeah, so this is the idea. So you can even couple, if you just stick to the mechanical solver, yeah, you can even couple finite element with SPH, for instance, or finite element with EFG, or so on. Yeah. You can then couple mechanicals to fluid mechanics. Yeah, say you have a structure which is deforming, the change of the geometry is changing the fluid flow, which changes also the pressure fields, which again changes the load on the structure, which again changes the deformation. You can also cover this with thermal solver, like you're having heat generated, maybe due to some plastic deformation. You can couple it with the fluid solver. That means the heat is then taken away by the fluid solver. Yeah, so just like cooling down, I mean, maybe a battery which is heating up, for instance. Yeah, these are applications. And this is the idea of this one-code strategy. And the good thing is it's very modular. Yeah. So you can just build the independent models, or you can build the models independently, and then just link them together through a keyword. Okay, here's an example of the SPH method. Here I'm explicitly talking about SPH coupled with a finite element method. For instance, this is a ceiling. We have the grease inside. The grease is modeled by the SPH method. The deformation of the structure is modeled by finite elements. You find this example also on dynaexamples.com. And you can somehow, this is rotating, and then you can compute, okay, how is the grease distributing when it's rotating? Do I have enough location of the structure? Yeah, you can see also here how it's interacting with the deformed structure. or here free surface flow, which is what you actually get for free from the SPH method. If you want to do the ICFD, you have to introduce level set functions and so on, for instance. It just requires some extra work. Here's another example. And this is actually an example which is, when you want to use this one, you should refer to the latest version you can find from LS-DYNA, because there was a bug in earlier versions. Actually, a customer figured this bug out. Then it took us a while, then you fix it. And the idea of this one is that we're going to do failure analysis of a structure. So this is a Taylor beam. So we're going to compress the beam on the wall. Just squeeze it. And then you get this, cone-like shape here on the bottom. And what we want to do is when the solid elements, the solid finite elements exceed a certain deformation, we want to replace them with SPH elements in order to proceed with the ongoing large deformation. So it's a mix between finite elements. Once the finite elements fail or reach a certain critical value, we're going to replace them by SPH elements and then continue the simulation. If you look closely on this example here, you can see that the SPH elements are already generated. This is done by a keyword, so you don't have to do it as a user. It's just as a keyword. I think it's solid to SPH. I have to check in the manual. I don't remember exactly, which creates the SPH elements. You can define how many you want to have. If it's one SPH per solid, maybe you want to have 2, 3, 4, depends on you. But in any case, they're already there, and the information like stresses are transferred to the SPH elements. And you do a simulation, and you can see that how the data is transferred. And at the very beginning, the data is just transferred. The SPH elements are not part of the computation, actually, just the data is transferred. But once the finite element fail, then the simulation is continued with the SPH element. Okay, so it's a bit hard to see, but if I check here, so I'm just taking a look from the bottom, this bar, and I say, so you get the deformation here, you get this cone-like deformation here, as you can see, and at some point you will see that the finite elements will fail. Let's continue deforming, and it will fail at some point. And you can see that the SPH element will keep the stress information, and then you can continue computing. So this is a nice feature, actually, especially when regarding failure analysis. Other examples, these are quite common examples, is bird strike, for instance, if you're working in the aerospace industry. And the idea is actually not to exactly model whatever is impacting the blades. It's just, the idea is just introduce energy into the blades. So just create some impact here, so create some loads. And this is mostly done with SPH method. Or another example here, high velocity impacts. Here you can also see we have a coupling between SPH and finite elements. So we have this structure here is modeled by finite elements, and inside of this one you find SPH elements. These are coupled by tie contacts. You have here some projectile modeled as SPH. It's impacting, and then we get a scattering of the particles of the structure. This will also be done very related with some experiments, and there was a quite a good agreement. However, I don't know how old this experiment was. But just to give you a general idea what you can do with this. For another example, this is an example for material mixing. There's a process called friction stir welding. I'm not sure if you have heard about this one. And the idea is you have two parts, two materials, which are separate parts, and you want to weld them together. And what you actually do is you generate some friction, which is heating up the materials, it's melting the material, and then you just go through the material, like if you bake a cake, for instance, when you're mixing the dough. It's quite similar. It looks, can take a look on YouTube. You'll find a lot of videos regarding this one. And to my opinion, it looks pretty fancy and out of this world. Because you have a metal and you're going to liquefy the metal and then melt it together and you mix it. Okay, anyway, this is the process. You have a spinning structure here, and then you use this one, spinning, and you're going to mix the materials, and then you're creating this welding line in here. You also, of course, you have some heat generation, which you can see here. Okay, this is some example of the SPH method application. Okay, so how does it work? I just keep it to the very basics here. In general, when we're talking about the SPH method, we're going to refer as a numerical method. And the idea of any numerical method is to solve a partial differential equation, right? So this is your top partial differential equation. This is your momentum balance in this case. You have this equation, and you want to find the displacement field which satisfies this equation. And in order to solve this one, because in general you can't solve it by hand, by analytical solution, you need to discretize it. And what you actually do in the discretization, you do two discretization steps. The first one is a discretization in space, which is going to resolve the spatial dependencies. Yeah, so what's the displacement at this location, what's the displacement at this location, and so on and so on. This is the first step. The second step is the time discretization. That means how does the location of an individual discrete point change over time. Yeah, so you have two discretization steps. One accounts for the spatial changes, the other one accounts for the time and temporal changes. Yeah, these are two methods. And I always, when I do courses, I always point this out, because just remember, me as a student, I had no idea. I was always, finite element method is simulation method, that's it. But also finite elements is just a spatial discretization method. And you can mix the spatial discretization method in general with any time discretization scheme. Yeah, so just keep this in mind. So spatial discretization method could be finite element method, could be elementary Gajerkin. By the way, there's also another webinar, introductory webinar, you can find on YouTube. And smooth particle hydrodynamics is also a space discretization method. Yeah, it has nothing to do with time integration, it's just about space discretization. And then on top, we apply a time discretization scheme, which could be explicit or implicit, and so on. Yeah. For smooth particle hydrodynamics, just for your information, the implementation at LS-DYNA is purely explicit. Yeah. There is an implicit method, which is quite new, but the default implementation is explicit, with all the advantages and drawbacks that come with the explicit scheme. Okay, so finite element fails, finite element analysis fails at large deformation. That's why we're going to switch to particle-based method, or to be more precise, to a mesh-free spatial discretization method. Okay, and one of these is the smooth particle hydrodynamics method. Like I said in the introduction, the SPH method is a discretization method for continuum mechanical equations. Yeah? And please don't confuse this with real discrete element or real particle methods. Yeah? So if I compare this one, so this is a particle method. By particle method, you have indivisible particles following the momentum balance, but the particles are interacting through like contact. Yeah? You have a Hertzian contact, particles are bouncing to each other, bouncing back again. That's how they interact. Yeah? In a continuum-based particle method or continuum-based mesh-free method, you still have the balance equation describing a continuum. Yeah? And you just use this method to discretize your continuum structure. Yeah? So here you have a continuum. You decompose your continuum into particles. And these particles can move independently, but still they represent a continuum. That means each particle is somehow connected to its neighbor elements, or a couple of neighbor elements. So there's some kind of smoothing out into the neighborhood. Yeah. Here you have just a discrete coupling between one node and another one. Yeah. Here one node is interacting through the continuum mechanical balance equations. Yeah. Yeah. So we have a continuum in our mind. Okay, so this is how it works. Decompose it into particles, and the particles serve as some kind of computational points in order to evaluate what is the stress field in this body if I apply a load. There are different methods available, or here again, smooth particle methods. This is a patch of SPH elements. Yeah, you have a plate, you have a stamp, and you try to forge this one. Yeah, you can model this one, and here we're going to describe this as a continuum mechanical equation. Yeah. On the other hand, discrete element method, it looks exactly the same. Yeah, yeah, you can see it looks quite similar. However, here we're going to compute individual particles which are interacting through surface forces with each other. Yeah, particles bouncing, contacting. You get some friction between particles. Yeah, this is something what you don't have here. Yeah, here you have discrete particles. Here it looks like discrete particles, but these particles are just serving as computational points in order to evaluate the displacement field. Yeah, so just keep this in mind. Yeah, SPH is not a particle method; it's a mesh-free method for continuum mechanical balance equations. Okay, so what's the basic idea? I think if you're into SPH, maybe you heard it already. So the idea of the SPH method is, first of all, decompose your structure into computational points, which are the particles. You define a so-called support domain, and then all particles inside of the support domain influencing the particle you're considering. Yeah, that means if you compute a stress for this one here, then you have stress contributions from all these particles within the support domain. Yeah. The influence is computed by a so-called kernel function. In theory, it's just a direct data. However, you want to smooth this one, so you want to distribute this to the left and to the right in order to have neighboring particles influencing this particle here. So this is how your continuous differential kernel function looks like. Yeah, you have more like a bell-shaped function. Yeah. And with this one, all particles which are in this range here are influencing the particle you're considering. And from that, you can build up a system of equations in order to discretize your structure in space. Okay, then you end up with some equations. You can recompute a displacement field based on its kernel function and so on and so on. The same applies for the gradient, which, for instance, is important for stress computation. Yeah. And yeah, so this is the basic idea. And this is how we end up. Yeah. So for instance, this is the balance of mass. You can discretize it with SPH method. You get something like this. You can do the same, apply the same for momentum balance and also for energy balance if you want to consider heat conduction, for instance. Okay, this sounds pretty good so far. Yeah, so let's use SPH method for everything which finite element method is failing. However, there are also some drawbacks. I mean, nothing is for free, and there is not yet at least this ultimate numerical method to solve differential equations. Also here we have some drawbacks. One of them is the treatment of boundary conditions. Yeah, if you think about, so let's say this is your domain. Yeah, so you have a couple of particles. So each peak here represents a particle. There's one here, giving this peak, another one here, this peak, and so on. And the response of the field you're going to approximating, yeah, is the sum at each location of this individual bell-shaped functions of the kernel functions. Yeah, so if you sum this up, you end up here. However, when you go to the boundaries, you can see that you're missing the other part of the bells. Yeah, and this is what you have here. Yeah, this is the problem. You cannot reproduce exactly the boundary condition because there's missing a little bit. And this is an intrinsic property of the SPH method. However, this is nothing what you as a user have to think about. Yeah? When you do simulations and you want to exploit symmetries, then of course you have to create ghost particles, and this is your symmetry plane, for instance. Then you have to create ghost particles here in order to have proper approximation. There's a keyword in LS-DYNA for that. I think it's called something with boundary, boundary ghost something. There's a keyword for that. Yeah, but this is something usually only when you think about symmetries, you have to think about it as a user. In general, yeah, the code is doing it in a proper way. Okay, but there's something more important which I want to point out, which affects you, or what you have to think about as a user. The thing is the lack of consistency. Yeah, so like you see here, we cannot reproduce a constant function, yeah, because of the lag. And if I even zoom in, I find something like this here. Yeah, I mean, here it looks like a flat curve, but unfortunately, this summation here does not give me a flat curve. No, it gives me something like this. Yeah, you have all these small buckles in here. Yeah, you don't get a smooth solution. And to compensate that, you need to apply really normalization. Yeah. When you later on talk about how to set up the simulation in LS-DYNA, you will find that there are some kernels which have renormalization, others don't have it. So in general, we recommend our customers to use renormalized kernels because they give a smoother approximation. However, sometimes you run into problems because they're tweaking the response or changing the kernel function a bit, and you may, for instance, end up with some negative densities or somehow. Yeah, this is just a little tweak to get a smooth approximation. And just keep this in mind, but I come back to this later on. Another thing which is really important to point out, and this is one of the general drawbacks of the SPH method, it's something called tensile instability. Yeah. So what does it mean? Yeah. So here we have a punch test. Yeah. We just have a plate here. We just, let's say, put it down, move it downwards. Yeah. What you can see is that you will find here some element separation. And you can see that we can move down these elements here. However, it looks like the element or the material is failing. Yeah? But actually, this failing is not physical failing because of the element properties. The failing is due to the SPH method. Yeah? So the SPH particles do have the tendency under tension. This clustering is prone to clustering. Yeah? You have the burst clustering tendency. That means if you tear them too far apart, yeah, and let's say you have a particle here and you pull it too far away, then this element becomes too far away from the influence, yeah, on this particle, and then suddenly you get a rupture. Yeah? And this is the tensile instability. Yeah, and that's why I pointed out, because you find it quite often in simulation that you find a premature failure, which is just due to the SPH method, but not part of the element properties. Yeah? Keep this in mind. So how to deal with that? Again, it depends on the kernel you're using. Yeah? There are kernels which are at least weakens the effect of density instability. Some kernels don't even have it, but I come back to this later on. So for the moment, I want you to keep in mind what is tensile instability. Yeah? And this is this clustering, this premature failure of the structure. Okay, now let's say, okay, you have everything, you want to start SPH with LS-DYNA. First of all, what you need to do, you need to create your SPH elements. Yeah? And I think there are different ways of doing this one. I'm just showing you one way, and this is the usage of LS prepost. What you can do is you have different options. You either have already a finite element model, and what you can do is you just convert the nodes of the finite element mesh into SPH particles. This is one way, or you create a hull, yeah, made of shell elements, and you're going to fill SPH elements inside. Yeah. In any case, the comment you need to use is quite similar. So when you use LS prepost, you go to FEM, you find it up here, go to element mesh and SPH generation, or you can also find it here somewhere. If you click here, you find also the SPH generation command. And then you can choose a method, and then you can choose either shell volume or you can solid nodes. Yeah, then you just select your structure. Yeah, you get this one here. You can insert a pitch. So what's the distance between the elements? Then you set the parameters. Somewhere here, important. You have to click this one, and then you click on create, and you get this. In this case, this hull filled with SPH elements. You click it, and then this is how it looks like. Yeah, I mentioned this because this is quite common request when in our customer regarding customer support. So now we have it. Yeah, we're going to also publish the slides so you can have a look later on, and you can create your SPH model. Okay, then you save it, and what you get is in the keyword file is something called asterisk element underscore SPH. You get a node ID. Yeah, so first you create nodes, and then each node is assigned one SPH element. What's the part ID? And then you can assign a mass to it, or you can also make it negative, then it's a volume, and then the mass is computed from volume and the density associated with this part. Yeah, so this is what you find in the keyword file. What I now want to point out are a few control keywords. And I'm just picked a few of them. There are many more to choose from. I'm just addressing a few of them. Most of them, or why I choose them, is again related to our customer requests or the support requests we get. Yeah. So the first thing I want to mention is this is mostly performance and stability affecting parameters, and there's a keyword control SPH. And the first one is number of time steps between particle sorting. Yeah. This is something to do with contact tracement, contact treatment, also performance regarding MPP, for instance. Another important one is the box ID here. So what you actually do is in SPH computation is, or what you may have is you have particles. If you have an impact, then you have all the particles scattering everywhere, right? But at some point, what you look at is just a small portion of the entire domain. That means if a particle is leaving a certain area, you don't care about anymore what this particle is doing, yeah? And the area of interest you can define with box ID. So that means every particle which is leaving this box is not part of the computation anymore. So with that, you can speed up your simulation once a particle is out of this domain of interest, so to say. Yeah. You also can start and stop SPH computation by time. Yeah. Let's say at the beginning there is no I don't have effect of SPH, so I'm not computing SPH particles and just started at some point when SPH particles become activated. Yeah. That's also part of increasing the performance of your deck. Another one is this max V here. No, it's not max Y, it's max V. So by default, elements which exceed a certain velocity are deactivated. Yeah. And this is sometimes what you see in the simulation. Sometimes you do an impact simulation and then some particles are just getting out of the bulk and going somewhere. Yeah. And most likely these particles have already been deactivated at some point because their velocity was exceeding a certain value and then became deactivated and not part of the SPH compound computation anymore. Yeah. This also, why we do this is because of stability, yeah, and also the performance, but mostly stability. Yeah, so just keep this in mind. I don't know what is the default value for this one. I'm not sure. I have to check in the menu. But anyway, I'm just pointing this out because this is a common question we get in the support. Okay, here we're going to talk about the form. Yeah, and the form is the kernel shape. Yeah, if you remember, just recall what I told you before about tensile instability. Yeah, this is why you're addressing tensile instability. In general, when you talk about the kernel functions, you distinguish between so-called Eulerian and Lagrangian kernels. So what does it mean in general? So this is your initial domain, your initial configuration. You have a particle, you have a support domain, and Lagrangian and Eulerian support domains are exactly the same. However, this is not drawn well here. When you now deform your structure, is in an Eulerian kernel, yeah, the particles inside of this domain is changing because you're stretching. Let's say you do take this one here, you stretch it, and you can see that some of the particles are moving out of this domain here. So that means Eulerian domain is a fixed kernel, so spatially fixed kernel, and you just have particles moving in and out. Yeah, but the shape of the kernel stays constant. Yeah, and this is in contrast to the Lagrangian kernel. The Lagrangian kernel is the shape of the kernel is adapted according to the deformation. Yeah. And with that, you can somehow weaken the effect of the tensile instability because the kernel, as the structure deforms, you can you try to keep the same number of particles inside of the kernel, yeah, which is a method of weakening the effect of the tensile instability. So this is a general difference. I don't want to go in detail of all these other kernels. Yeah, Eulerian, Lagrangian kernel. And there are even enhancement method. Most of them are related to how to cope with the tensile instability. And there's another one, which is commonly used for structural deformation, is the adaptive SPH method. Also here, the Lagrangian kernel is deforming, but the deformation is adjusted based on how the deformation is, in which direction. Yeah, so it's more like there's an anisotropic tensor in it, which is governing the shape or adjusting the shape of the Lagrangian kernel. And that way, where we have large change in geometry, we're extending the geometry, and we do not do in the other directions. Yeah. So this is the idea of this adaptive smooth particle hydrodynamics. Another important one, and this is a quite recent one, I suggested you use the latest version of LS-DYNA. I think R12 is right now. And there's another one which is called the moving least square kernel. And this kernel is doing it a little bit different. If you recall, I told you the tensile instability is an intrinsic property of this kernel, the bell-shaped kernel function. So what this one is doing, instead of using Gaussian or this Gaussian bell-like shaped kernel functions, it's going to replace the approximation inside of the support domain by an arbitrary polynomial. Yeah. So I think the default it's a cubic or quadratic polynomial, and it's trying to fit the particles by a least square minimization, so that we're not going to use this Gaussian function for the approximation, but rather a polynomial approximation. And this is very favorable if you have large deformation. And this gets mostly rid of this tensor instability because we don't have this bell-like function anymore. Yeah. So these are just a few marks regarding the kernel functions. I mean, you can also take a look on the manual. You find more elaborate explanations. Also, can you go check out DYNAlook to find even more information regarding this one. Okay, another few remarks. Also, again, this is the idea where I brought the slides because of the support requests. In control SPH, you find a parameter which is called EIVIS. And IVIS is, I don't know what I is, but it's artificial viscosity. And like many other methods which are dealing with high dynamics, like impact problems, in explicit, you always have impacts. And then every impact is introducing a wave propagating in the system. And that actually what it does, it creates some kind of numerical noise. So that's why we use always some kind of viscosity in order to dampen out these dynamic effects. And what I want to point out here is, by default, there's a method behind this one, which has a certain amount of damping in it. But some people which do the simulation properly, they run the simulation and then they do as what we always say, do your simulation, check the energies. And what they then notice is they find energy dissipating. Yeah? And then they send a support request, why is the energy dissipating? And the thing is, when you have strongly nonlinear effects and you're checking the energies, and sometimes this default values for the viscosity, which is always active, is too strong, and you get a drop in the total energy in your system. Yeah. So what we recommend when you run a simulation with fluids, we recommend you set this AVIS to 1 and then choose these parameters in control solid. Yeah. This is this is a recommendation in how to weaken the effect of this intrinsic or built-in artificial viscosity in the SPH simulation when you work with fluids. Yeah, with solids, you should work with the default values regarding this initial artificial viscosity. If you run fluids, we're going to recommend this one here. Yeah, choose the method number 1, which is the standard type, and then choose these parameters in control solid. Another parameters regarding SPH contact, you can activate or deactivate contact with these parameters. I'm not going through them. I'm just pointing out if you want to have contact, just be careful. I mean, there are some parameters to activate or deactivate it. Okay. Okay. Let's move on to the section SPH. Also here you need a section definition, and here we can define the smoothing length. So what's the size of the impact area if you can look at one particle, you can apply some scaling factors. The smoothing length is computed automatically. You can choose some parameters here. Also here again, you can redefine the depth and start of the SPH approximation. Yeah, I think this is a more local value. If you use the one from control SPH, this is global, applies to all the parts, and here you can somehow start and stop the SPH approximation on a more like a part-like level. Okay, with that, I'm almost at the end, giving you a small introduction. However, I also want to address one of the recent or most recent updates in SPH simulation, and this is an implicit SPH formulation. So we want to do SPH for implicit time analysis, and usually this happens when you have something which is not a short duration event. When you have explosives, impacts, and so on, you go with explicit because this is what explicit schemes are beneficial. However, when you want to do something slow, then you rather use an implicit formulation because then you can go a larger time step, and it's more efficient. And one of these examples using implicit and coupled with SPH, so-called weighting simulation. Here we see the 3D rendering of this one, and here we see the particle deformation of this weighting simulation. Here's another example. We have also introduced, or the guys from LST have also introduced the so-called wetting factor, because this is something what people want to know when they do the wetting installation. How much, if I have a structure, to how much water this structure is exposed. So I do a wetting simulation, I have the car, in this case, running through some pit of water. And then I want to know, okay, how much water, or how much the structure got exposed to the water. And then we have this wetting indicator, so the car sitting down, going down. We have the structure, and you can see, red, it's high exposure, but blue means no exposure. Okay, to wrap this up, we have seen SPH is a mesh-free method. Please don't call it a particle method, it's a mesh-free method. It's a mesh-free method to solve continuum-based differential equation, different equation based on continuum mechanics. SPH is just one step in the entire discretization scheme. So it's first spatial discretization doing SPH, and then we have to do a time discretization. SPH is superior to FEA when it comes to large deformation, material separation and mixing, and when it comes to free surface simulation. However, like I said, there's also a drawback. Usually it's more computationally expensive. And as we have seen with this lack of consistency, has accuracy issues with the more efficient implementation. So the more complex the kernel function becomes, for instance, the moving least squared kernel function is very accurate. However, it's very time-consuming to compute. So this is always the issue. There's not such a thing as a free lunch. So the more accurate you become, the more computational power you need. This is usually the trade-off you have to do. With that being said, thank you for your attention. Here are some resources I would like to address. DYNA support, you find many common FAQs, tutorials, not only regarding SPH, also implicit guidelines we have there, for instance, which is commonly used. DYNA examples is a good starting point. DYNA look papers from past conferences. Check this one out. It is pre-post, you can get for free here. And then, of course, you find us on YouTube. You also find, we're going to find this webinar on YouTube later on, together with the slides on our homepage. If you have questions, feel free to contact us, support at DYNAmore. With that being said, thank you for your attention.